Okay. But hold on. This is not connected. Okay, yes. Okay, so how about I quickly go over the diagonalization here and so you did not get the matrix itself, or you couldn't get it to work.
I got the matrix, I mean, eigenvector and everything, but I couldn't get the last expression, I mean, the diagonalization expression. I couldn't get the matrix actually. Maybe this matrix is not actually diagonal.
No.
It is.
This is a very popular matrix. Like this is the angular momentum diagonalization matrix. So no. This is
I did it with
Mathematica.
a program. Well, I used Microsoft Math. It's a program they don't even do anymore, but I have an old copy, and it does a lot of matrix stuff.
And it
So
gave you the
well, and I multiplied it in this order, and it came up with a mess, and then I had it reduced, and it reduced to 1001.
So that means this is correct then. It's
Yes.
just that you're not able to show it.
It's just that I'm not able to show it, and that bothers me.
Good. Okay, so because I think last time I went through in a hurry there because we didn't have too much time, so it is good to get this done. Okay. I'm just wondering which one to do. Should I do the homework one or the last class one? Homework, because you guys have all worked on it, so probably it is fresh in your head, right? And I haven't put the new homework. Look for it today, and next Thursday is the exam. I should write that down. It's not a Friday. I hope I don't forget it more than you guys. It's not a midterm too, so no homework at this point, but it's due November, not due, November 4, Thursday, 5 p.m. Make that. And there'll be a homework 8. It won't be due before this, but probably the Tuesday following that. What's that Tuesday? 9, right? Number 2 is Tuesday plus 7. So that's tentative. I haven't.
You mean 9?
Oh, I said it.
I have a horrible habit of doing that when I'm saying something
You're thinking.
in writing. I will just say what I'm writing and write what I'm saying.
Yeah. So that can have it. Yeah. So that's matrix. Yeah. So let's that. Okay, but you have to help me. So the matrix, I suppose, let's call it A. Let's call it A. This is a special matrix. We could call it sigma. Okay, so this is cosine theta. Oh, this is the one. I didn't realize I did this. And eigenvalues are plus or minus
Plus
one.
minus,
Plus minus one.
So A prime, right? So plus or minus one. So prime, or so in my notation, it's not a standard notation, but Dirac introduced it, but no one followed it, I think, and Schwinger follows it. So I try to be consistent. So prime is the eigenvalue, and the eigenvector associated with A prime is equal to plus one is equal to something. Oh, you guys submitted, so you guys don't have it in your head.
Cosine theta over 2, sine theta over 2.
Cosine theta over 2.
Sine theta.
Sine over 2, that's it.
Yeah.
And that is a e raised to I alpha.
It was, oh, I didn't get any imaginary.
Yeah.
Huh? What?
I put
It's, there's another one that gets an imaginary eigenvalue. This one is real.
No, this is not eigenvalue. This is an arbitrary space.
0 equals.
Any eigenvector, any matrix will be off by a phase,
Okay.
right? Every time you don't have a choice there, right? As far as their complex numbers, because we are working with complex numbers that are allowed. This will always be there. Remember, I mean, I think I went through it in detail last time. Okay, let's do this quickly. Okay, so let's derive this. I'm back. Okay. So how you would do this is lambda, right? So it's plus or minus one. So minus one, right? So it is cosine theta. I'm doing plus one, so it is minus one sine theta. Sine theta and minus cosine theta minus one. And you have to multiply it with some complex number, notice Z1, right? Times Z2 is equal to 0. That's our condition. Right?
How do you know that the eigenvector will be complex number?
If it is real, it will come out to be real. Like, let it be complex. If it is real, it will come out to be real, right? Real is part of complex numbers. Right, so good point. Yeah. So at this stage, there is nothing that tells that what is the whether it is complex or not, but you allow it, and if it is real, it will come out to be. So in that sense, it's okay. Yeah. Yeah. Good point. I mean, when you're doing quantum mechanics, there are some restrictions on that. It does come out to be complex, and but here this is just a matrix, so you allow it. I mean, if it is there, if it is complex, you let it be complex. Yeah, that's okay. See, yeah, yeah. I don't see any other better answer there. Yeah, but yeah, don't accept my word on it. Okay. I might be missing something. Okay, so before we proceed, should we do, I simplify this somehow? Yeah, so let it be as it is. And now I put this equation, right? So I have cosine theta. So the equation is cosine theta minus 1 times Z1 plus sine theta times Z2 is equal to 0. So that's first equation. This one will also give the same equation. It will not give anything else, but we are trying to make it normalized. So that's where I was trying to point out the imaginary phase I was saying, right? If we are normalized, we say Z1 squared. So normalized, because it's a complex number, that's squared plus Z2 squared is equal to 1. So that's your two equations if you want. Let's go back to this equation, and I can use 1 minus cosine theta is 2 sine square theta over 2 times z1, and this is plus 2 sine theta over 2 cosine theta over 2 z2. That's using trigonometric identity. Yes, question.
Cos theta minus 1. It should be 1 minus cos theta.
I was wanting to do that. But thank you. Okay. 2 cancels out, sine theta 1 cancels out, and then what we have is sine theta over 2 times z1 is equal to cosine theta over 2 times z2. That's it. A relation, or you can say z2 is tangent theta over 2, right? So this immediately says that z2 is tangent theta over 2 times z1. Put that in this equation. Remember that this is magnitude, that is where that imaginary part is hidden. So this is a magnitude. So you say that tangent square theta over 2 times z1 square, z2 plus z1 square is equal to 1. 1 plus tangent square theta over 2 is secant square theta over 2. So this is z1 magnitude z1 square secant square, and that's equal to cosine square theta over 2. That's clear, right? But this only tells us that z1. So this implies that magnitude of z1 is cosine theta over 2. Plus or minus is also there. But then what does that mean? Z1 could be having a face, right? A complex number whose magnitude is this much. It could have any face associated with this. So you say that this is e raised to I, since it's 1, I call it alpha 1, and cosine theta over 2. You would say that when I went from here to there, there's a plus or minus involved, but that's okay because you can absorb that into that face, or you can say that magnitude is always positive. So that's also another way of arguing. So that's your z1. So that face is always there as far as you allow complex numbers. Again, going back to the question, if it is not a complex number, then that face is not necessary. But in this way, we can always allow that. Right? We are asking all the solutions of this equation. Z2 is tangent theta over 2, right? So we just have to multiply that. Z2 is this multiplied by tangent, so that makes it a sine. So this is e raised to I alpha 1 sine theta over 2. So our eigenvector, we write like this, is equal to e raised to I alpha 1 cosine theta over 2 and sine. That's the first eigenvector. Do the same thing for the second one, which I will take from you guys. Like, is that clear why that alpha is sitting there? It will always, almost always, there is an arbitrariness in there. You would ask, oh, what happens to that in quantum mechanics? And this never gets fixed also, by the way. You would think that, and this will show up in some physics. No, because when you square, wave function square is what is mentioned, not the wave function itself, right? So when you square it, that goes away. So to my knowledge, this is not measurable. This has no measurable consequences to it. But having said that, one should always remember that all the new things that if you want to do something creative and come up with something new, then this is where you want to look for. So there is an experiment and you're not able to explain it with something, then always these kind of things, which is arbitrary, it has no observable consequences. Maybe we are missing something. And if you can be clever and measure this, then that's cool. That's how new things happen. But to my knowledge, that's not having any measurable consequences. This is like sometimes you also say it is like a gauge, right? Gauge, have you gauge transformations in electrodynamics?
Mm-hmm.
So you can shift an electric field given in terms of the potentials by a certain amount, which is a function, and still not get anything. So it's very similar to that. And not exactly this one, but that is what is called Berry phase. Like that's in topological insulator that plays an important role. There it comes out as a phase, but to my knowledge, it is not this phase. It is not the phase that is coming in the eigenvector. So sometimes the phase plays a very important role, even though it is not. Often we say that it is not measurable. Another place where the phase really makes an important role is Dirac quantization, where you say that electron times the monopole is equal to some h bar times the number. Again, what he says is that usually we drop this phase, or phase has no measurable consequences, but he said, yeah, but alpha 1 could be 2 pi n, right? And that might have observable consequences. And that's what his postulate is regarding Dirac quantization. But so what I'm trying to say is that, yeah, phase is in this, it is not measurable. So if you're really clever, maybe there are places where you might have consequences. Okay, so that's for the first. So now the notation is there clear, right? The eigenvector corresponding to the first eigenvalue. So this is e raised to I alpha 1 times cosine over 2 sine over 2. And the second eigenvector is prime equal to -1. Okay. So one should come up with a better notation, but I don't know how to make this simple, so we don't have to write the whole equal to +1. But that's all. That's the best I can do. What is the vector here?
It's
Sine minus sine theta over 2 or sine theta over 2?
a minus.
Minus sine theta over 2. It's e raised to I alpha 2. Is there a way we can quickly check that? Cosine theta, sine theta over 2. Let's see it. You guys all got the same, right? You guys remember it?
Yeah, like
Okay, we'll worry about it.
I don't know about that minus.
Okay, we don't know. Okay, so let's check it then. So quick check, right? So this should be sine theta minus sine theta times minus sine theta. Phase doesn't matter, right? It completely comes out. Minus sine theta over 2 cosine theta over 2. In this check, the phase doesn't come.
0.
Huh? 0.
Like should be 0.
It shouldn't be 0, right?
No,
It should give back. So this is cosine theta sine. Why is it there? It shouldn't be 0, right? It should give me back this. Right? Is it 0?
No,
Plus
full angle and half.
cosine theta over 2 and sine minus sine theta over 2 and minus sine theta cosine theta over 2. So we can use the. So this is sine theta, sine A, sine B. Sorry, sine A cosine B, and so this is sine of theta minus theta over 2. With a minus, no, this is sine of theta minus theta over 2. That's all. Okay, right? Theta minus theta over 2. And this is minus of cosine of theta minus theta over 2. Right. And this was a minus eigenvalue, right? So that's correct. Right? So this is equal to minus sine theta over 2 cosine theta over 2. Eigenvalue times the eigenvector, right? So that's correct. Yeah, any questions? Okay. So now we want to check it. Okay. So the idea is that you put the diagonalization matrix in the front, right? So there is a matrix in the front, then there is cosine theta, sine theta, minus cosine theta. And in the front, keep these eigenvectors because this applying on the eigenvector gives me back that eigenvector itself with the sign. So put that as column matrices there. Probably it can be put on the other side also, but at least I remember a couple of times I got stuck with it. So I never verified it. So as a theorem as to whether it is, it matters to put it one way or the other way. But surely this way I know because this applying on that gives me back the vector itself as far as the column. So that's a good. One can do this with the phases also, but remember it was an arbitrary phase for simplification. Let's keep that out, like just for simplification, because if one is true, then anyone should be applicable. It's just more messy because there is alpha 1 and alpha 2 sitting. Okay, so this is cosine theta over 2 sine theta over 2 minus sine theta over 2 cosine theta over 2. And you want the inverse of this. This is a rotation matrix, right? So it should be just the minus replacing the opposite. I think this will be just this. Okay, we can check that cosine square. Sine square is 1, cosine is minus 9. So yeah, this is the inverse matrix of that. So that's just a rotation matrix.
You divide it by the determinant.
Determinant is 1 cosine square plus sine square. So determinant is 1 because this is a rotation matrix, so it should work out. Right. Clear? Okay, so now
I think if you put those phases in,
that is
that because of the fact that the inverse also has to be a conjugate. So that would get rid of those anyway.
no, right? Because sorry, I wrote it. No, this is alpha 2, right? They're not the same phase. Is that what you meant, or it'll always work out? You're saying?
I was going to say that I guess you're right. I think because
it's a little messy, but eventually at the end they will all go away. You're right. They will all go away. I have done this once with all the phases in that, and and what I'm saying is that in a classroom sometimes simplicity helps because you're seeing through the concepts also. So it doesn't really help a lot. There was I think I used to worry about it a lot a few years ago because its topological insulator was very much there, and I was trying to understand it in those days, and I was associating Berry phase with that. I was thinking that it's Berry phase in that, but then my conclusion eventually was that it's not really this. It does come out as a phase, but not this phase. It's not the eigenvalue. So I think there is not much in there. So if you allow me, let's keep it. Because I'm trying to convey the point that how do you build a matrix. So then extra credit. No, let's not. No, I don't want you guys to. That's a little lengthy. You know. Okay. So do this cosine theta over 2 minus theta over 2. Sorry, plus. So this I keep intact. Just blunt multiplication, that's all. This one, cosine square, this is cosine theta sine theta, that's like cosine A, cosine B, right? So this is cosine of theta minus theta over 2. Cosine theta. This one is minus, let me start with this, right? So it is sine theta minus theta over 2. And this one sine theta cosine theta. And this is sine of theta minus theta over 2. And this one sine theta, so minus minus. So it is minus of cosine of theta minus. Okay. And it doesn't work for what? That's what you were saying, right? It doesn't seem to work. No. Okay.
Cos theta by 2.
Yeah, this is so. Am I missing a minus somewhere? Why is this fine? Because I want this to be okay. Can check this again. So this one, right? Cosine theta sine. So sine theta, cosine theta. Yes, this is not minus, right? This is plus, right? Can you check this for me? This piece, sine theta minus. Oh, no, it is. It is. Yeah. Okay. Whatever it is. Okay, that's what it is. So it is not working. Is that thing? You sure? Okay, that's cosine theta squared, sine theta squared. That's surely 1. The sine theta over 2.
The first one.
Oh, it is working. Right? 0. Correct. Okay, let me check it. So I'll write this again just for convenience. I think it is for a moment. Are you comfortable with this? Whatever I did, this one is that very clear? Right?
Yeah.
Okay, so that's cosine theta over 2, sine theta over 2, sine theta over 2, and this is minus cosine theta over 2. So that's equal to cosine square plus sine square, that's 1. Cosine sine with a minus sign, so it's 0. Minus plus, so it's 0. And oh yeah, this is okay. Yeah, I was thinking, why is it not coming 1? It's not supposed to be identity. Yeah, this is minus 1, correct? Which is good. Right, the eigenvalues like diagonalization, because I was thinking I have to get it 1, 1, and I was thinking, oh, that's not correct. Yeah, so this works. Yeah, is that clear? So maybe you were not getting because you were not putting it in the right place. We can check it very quickly. What happens if we put it the other way? Is that? But okay. To begin with, how do you do it? Get a diagonalization. Once you have eigenvectors, you put it as a column on the front side, not on the back side. That's we can check it very quickly. But we can. Yeah, I think this is only 3 steps, right? But let's quickly do this. Yeah. Any questions at this stage? Yeah.
There you get this equation z equal to 10 theta by 2 z.
How did I get this?
No. So in this equation, if I arbitrarily put any theta and z on, let's say I mean simple value, let's say if I take.
That's good enough.
But if I do this way and try to diagonalize the matrix, I couldn't diagonalize the matrix.
it should work. Because what you're doing that way is that you're basically changing the face.
Yeah.
The only thing you're doing that way is changing the face, and it should be okay. Let me see, think. Because there's one more thing that you're not normalizing it, right?
Let's say if I even normalize it, I mean, using
If you
algebra.
normalize it, then it has to work. Then it is an algebra mistake. And then I'm pretty sure, because if you normalize it, this is the only difference between your solution and what I wrote here is the face.
Should I have to use same theta in both of the solution? Because in another one I'll get cos theta by 2 and something like this. So should I have to use same theta in both of those eigenvectors or the equation?
Yes. Why would you choose theta? You will choose Z1, right? Not theta. Maybe that's the challenge. Theta is there inside the problem itself. What typically is done is there is an arbitrariness Z1. Right? You say Z1 is equal to 1. And Z2 is tangent theta over 2. But theta you cannot pick because then the matrix is fixed now, right? Then the matrix is a parameter matrix. And you're out of the whole parameter set, you're picking one kind of. So it will work for that particular angle, but not for the general theta, right? So that's the error probably.
Yeah, I actually choose theta,
Yeah.
theta too.
Yeah, because usually what happens is that when we, like most of the math classes or even everywhere, you never give a variable matrix, like you get 2, 3, 4, 5, like diagonalized, right? That's the typical problem. But in real life, when you're actually doing quantum mechanics, it's a variable matrix that you have. So I give this problem because I feel that, because this is what you'll come across in the next week. We will be doing exactly this matrix. The eigenvectors and eigenvalues, it has to be in your head if you want to analyze. So what we will be doing Stern-Gerlach experiment, it has to be in your head. This is angular momentum, Pauli matrices. The most general Pauli matrix, like all the 3 Pauli matrices are there inside this. Actually, there should be phase also there. There's a phi dependence also, I have killed it. Okay, so Pauli matrices, this is a very general Pauli matrix. It's called the Poincare sphere. All the Pauli matrices sit on it. It's also called block sphere. So that's a nice matrix in that sense. We'll come across it in a lecture or so if not today. So yeah, so that answers your question.
Thank you.
Any other comments, questions? Okay. So let's do the opposite, right? I'm just curious if that works or not. So let's put this here and that there. Does it work or not? So there's a chance that it may not work. So we have to sign theta over 2. Sine theta 2. And let's see, keep this intact. Sine theta, cosine theta, sine theta, sine theta over 2. So that's cosine of cos theta plus plus, right? Yeah, so maybe it doesn't work. Let's see. Let's go through. Okay, cosine theta, sine theta is this. So that's sine of theta plus theta over 2. And it's again sine of sine it's minus of cosine of theta plus theta over 2. Check. Okay. Is that okay? Yeah, if you see an error, let me know. I make mistakes. Okay, but let's see. So will this work? Maybe it's a drop. So cosine minus sine. Right. So this is cosine 2 theta, right? Minus so it doesn't work like this. Cosine sine plus, so it's sine of theta. Sine cosine. So, fine, right? Yes, it doesn't work. No. So yeah, so the order, so it has to be whatever eigenvectors. If you call this S, right, the matrix that you build out of the eigenvectors as column vector, then it is A S inverse is on the left. Yeah. Or if you call this S inverse, whatever you call it, it is part of that. Is that clear? I think this is like these are the stages when a computer or something like because I don't trust like even though to a certain extent I'm careful, but I can always mess up, right? So we go and check this out. Yeah, okay. So
Is there anything relevant out of the fact that the trace of that is 0?
the matrix is built out of those. Remember, Pauli matrices are traceless. So this is a traceless matrix to begin with, and yeah, why is the this also coming out traceless? So the fact is that I think I can tell that. So you have, if you say that, let's say that is a matrix A, any matrix, it doesn't have to be this, no 2 by 2, any matrix. Let's say trace of A is 0. Now trace is invariant under diagonalization matrix. So you can say if this is 0, you can ask what about this? What happens to the trace of this quantity? So that's the diagonalized matrix. Turns out that this is under trace of 3 matrices or 4 matrices, they're cyclic. Like you can put this back on the other side. Trace of matrices have the cyclic nature. So that's A times S inverse. That's equal to trace of A. So under diagonalization, the trace of the matrix remains the same, which is kind of interesting because trace of all the Pauli matrices is equal to, think of 3 Pauli matrices. Do you guys have it in your head? What's the trace of the 3 Pauli matrices? So one of them is 1, so sigma z is 1, 0, 0, minus 1, correct? What is sigma x?
I,
Right? That's trace of that is
0.
0. What is sigma y? 0 minus I 0, right? What's the trace of I? That's 0, right? Trace of sigma I, all three for any I is equal to 0, which means that its eigenvalues are, remember, plus or minus 1. After diagonalization, so this matrix is only that plus the eigenvalues come in a row, right? So they have to be plus 1 and minus 1. So if I tell you that there is a 3 by 3 Pauli matrix, like let's say that someone invented, tomorrow someone writes a paper that there is a Pauli matrix in a very high dimensions, let's say, maybe 97 dimensions, someone claims that they found a Pauli matrix. And immediately you would say, what would you say to that?
Couldn't have a trace of 0.
It couldn't have a trace of 0 if its eigenvalues are plus or minus 1. So there are two conditions we have found for Pauli matrices. One is that its eigenvalues is plus or minus 1, and that its trace is 0. So after you diagonalize this matrix, right, they will look like all zeros, right? And you have to fill in plus or minus 1 here in such a way that they all have to be 0, right? And with plus or minus 1 alone, can you get a 97? And the trace also has to be 0, exactly. If the trace is 0 and the plus or minus 1 alone, you cannot have a odd numbered matrix. It has to be an even number. So Pauli matrix can be 4-dimensional, can be 6-dimensional, can be 8-dimensional, but no odd numbered or just based on this argument. Right? But the smallest has to be 2 by 2 again because it's traceless, right? So since it's traceless, the smallest Pauli matrix you can do is 2 by 2. The next one is 4 by 4, and those are the Dirac matrices. Dirac matrices have the Pauli matrix in it, and they are the Pauli matrix property in the 4 dimensions. So yeah, that's it. Yeah, what's the relevance of that trace? What else is invariant under this? Like if you have a matrix that is traced, and another very relevant property is determinant. That also remains the same under diagonalization. If the determinant of a matrix is known after you diagonalize it, which means to say, after you find the eigenvalues, the product of the eigenvalues will be exactly the same. Right? Will be equal to the determinant of the matrix. So those are all nice little constraints on the matrices itself. Okay. Any other questions? Okay, so now we should know everything about diagonalization. So in exam, I can ask anything. So, since we spend so much time on it, so you can expect something tricky. Yeah, actually. So these are the questions I've asked in the exams before. How about that? So let's say I don't tell you anything, but I tell you that a matrix A cube is equal to 1. There exists a matrix. When you cube it, that's equal to 1. What are its eigenvalues? Plus 1. And?
also be plus 1. It cannot be negative.
No. And what's the argument you're giving? Those are matrices, right? A cube eigenvalues. How are you doing this?
1, 0, 0, 0, 1, 0, 1. let's see. No,
Explain, you seem to be thinking correct, yeah. Can you elaborate?
no, it didn't get much.
Okay,
It's really like that.
so again, based on the same idea there, right? So we have a diagonalization matrix. Now, I haven't given you the matrix at all. I have only given you that matrix satisfies this. I don't even tell you what's the dimension of this matrix. It could be a 97 by 97 order matrix. But how do you do this? We can multiply the diagonalization. So there is some S matrix. So let's say S inverse of A cube. I write A cube like this. A cube and S is equal to S inverse times S, right? Which is 1. I can do this again. S times S inverse. S times S inverse. And that's also correct, right? What can you say about S inverse A times S? This is a diagonalized diagonal matrix, right? If this is the diagonalization matrix of matrix A, this is a diagonal matrix, right? So let me say this is diagonal, which means that these are all eigenvalue vectors, lambda 1, lambda 2, all is 0. Correct? Okay. So what I have shown then is that A diagonal cube is equal to 1. Is that clear?
How do you get the cube?
Because this is AD, that's AD, that's another AD. AD, 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 and that's 1. So AD cube is 1. Is that clear? Because that's my definition. That's a diagonalization matrix. No? I'm satisfied. So I'm saying this is AD, AD, AD is equal to that's 1.
So I got it, but how do you get the right hand side?
Oh, what I did was I multiplied by S inverse from the left
Mhm.
and multiplied by an S from the right.
Okay.
So I had to do the same thing on the right also, right? S inverse S, right? But that is 1, so I don't even have to write that. And then I insert a 1 in between. Right? And this is a standard trick you use in matrix algebra usually, that you invert and introduce a 1 and then play around with it. Like you can.
When you multiply a diagonalized matrix, you just multiply the diagonals.
Correct, exactly, diagonals. And then there are eigenvalues though. So this means that each of the eigenvalues, lambda 1 cube has to be equal to 1, lambda 2 cube has to be equal to 1, lambda 3 cube has to be equal to 1. Correct? So that's the 3 equations there. That's the 3 solutions to the equation x cube is equal to 1. Right? If I have a polynomial, z cube is equal to 1, that's your 3 solutions, right? If I know lambda 1, lambda 2, lambda 3. What that means is that I can write any polynomial involving a matrix, any polynomial, any function, replace it with eigenvalues, they become numerical.
Mhm.
Eigenvalues also satisfy the same equation. So my question is very easy now. I have to find 3 eigenvalues that satisfy this equation. Numbers, no more matrices, right? This has solutions. Now this is a question for you guys. What's the solution of this? Again, you were saying +1, but that's not sufficient. Now we have learned a lot. What's the solution of this? There are how many solutions?
3.
3. Yeah. What are the 3 solutions? One is surely a solution
Mhm.
that I can point out. What are the other solutions? Because 1 cube is 1, right? What are the other solutions? No. You guys need to answer this. We have studied the whole of complex now. You did a homework.
I think omega and omega square.
Omega and omega. What is omega?
Root over minus 1 something.
Diagram? Think of a diagram. Like when these are roots, these are called roots of a unity. It's bad that you guys don't remember this. So draw a circle. This is 1. That's this point, right? Put the 3 points equidistant on a circle with 1 being already a solution. Right? So that will be here. So that's 120 degrees, right? And the other one is here. So those are the 3 points. So if you want lambda is equal to 1 is a solution. Lambda is equal to, so this is 30. 120 means that's 30 degrees, right? So that's sine theta over 2. So that's 1/2 plus I root 3 over 2. And another solution is 1/2. This is complex conjugate of that. Solution. Is that clear how I got that? Like take a
This is the minus 1/2.
oh yes. Yes. Thank you. Thank you. Thank you. You're completely correct. Thank you. Okay. What if I give you a matrix A raised to phi is equal to 1? What are the solutions? What are the eigenvalues? Lambda raised to phi equal to 1, and you make a pentagon out of that. Right. Again, 1 is a solution, so you know that 1 has to be there, and then you make a pentagon of that. So kind of another thing which I think another interesting thing is this is related to quantum mechanics. So we have, let's say, in Heisenberg's uncertainty relation for position or momentum is P comma Q. No.
X comma P.
X comma P. Right? So it does vectors. No, that's just one dimension, right? X comma momentum in the x direction is one dimension. And what is this equal to?
I bar.
That's equal to IH bar, okay, right? And this is 1, right? If you want to think of it as matrix or operator, so it's a 1 there, but let me, so this is a, now let's say, usually we say this is an operator, P is an operator, derivative d by dx, 1 over I d by dx, right? That's okay. But now let's say that these are matrices. X and P are matrices. And then the question comes, give me one solution for X and P that satisfies this. Okay, so that's an exercise one can do. But then I can do the following before you guys try to find out what is X and P. Let's do the following. This is X times P. These are matrices now. I'm claiming that these are matrices. X times P minus P times X is equal to IH bar, right? And if these are matrices, that's a unit matrix confined, right? That's it. That's the same statement written more explicitly. We can do anything with this. Let me take the trace of this this equation. Like this is a matrix. Trace is a sum, so it can distribute, right? So this is trace of XP minus trace of PX is equal to IH bar times trace of the unit matrix, like whatever the dimension of that matrix comes in. Okay. I just now use the fact that trace is cyclic, right? Trace of XP is the same as trace of PX. So that's 0, right? So this is 0 is equal, but this is the dimension of the matrix, right? IH bar trace of a unit matrix, that's impossible. That's impossible. How can a number be equal to 0? Right? So you say that Heisenberg, no, there's no solution to that equation. So Heisenberg quantum mechanics is wrong. So it's all, you don't have to do quantum mechanics, you just do classical mechanics. Right? Right? So what's wrong in this? There's nothing wrong actually. There's absolutely nothing wrong in this. But then how do you, what do you, if there is no solution, what's the point? So apparently, remember that we do have an operator solution, but we can have matrix solutions also if you allow. So, or the way to say it is that this will be equal to a number if this is a finite dimensional matrix. Right? You say that these are infinite dimensional matrix, and then there is a solution. So one dimensional Heisenberg uncertainty relation does not have a matrix solution if you say that the matrices are finite dimensions. But if it is infinite dimensional, there is a solution. And I do ask, maybe I'll put that as a homework. I mean, just as an exercise. It's good to know that there is a solution, because you don't want to feel that this is not that. It's sometimes even, I don't want to try to be like it's basically diagonal, but one you shift it off by one, but you are trial and error and get it. You don't get it in a, you cannot derive the solution. Okay, that clear? So that's kind of interesting note to keep in mind. Okay. 15 minutes. Okay. Tell you guys. Let me have a little bit of what I was planning to do. Maybe since there will be a homework. Okay. So these are Pauli matrices. Remember that even though Pauli matrices, we always almost everyone these days says that sigma x or sigma 1 is equal to 0, 1, 1, 0. Sigma 2 is equal to 0 minus I times 0. And sigma 3 is equal to 1, 0, 0 minus 1. But this is only one example of a Pauli matrix. There are many Pauli matrices. So what does that mean to say that there are many Pauli matrices? What do we mean by that? This is not the definition of Pauli matrix. What is the definition of Pauli matrix? It's any three matrices. So what is a Pauli matrix? Any three matrices. Any three matrices that satisfy the following. That satisfy so let me call them three matrices sigma I. Okay, so I is equal to 1, 2, or 3. First is that they should be traceless. Trace of sigma I has to be equal to 0. Second is, so this is traceless. Second is, it has to be Hermitian. Sigma I dagger is sigma I itself. Is dagger clear? You first take a transpose and then take a complex conjugate. It doesn't matter which order. Take a complex conjugate and then take a transpose or either. So this is Hermitian. Is there any other property I'm missing? Let's see. Got it? No, it's not doing that. Okay, I think that's, and it is also unitary, but I'm not sure if it is only the 2 by 2 matrices that are unitary or not. Not sure about the unitary, yeah. So any three matrices that satisfy that, they should be traceless, Hermitian, and the most important one is that this is called the algebra. They should satisfy, pick any two matrices, and if you multiply them, any one of these, the three matrices, if you multiply them, if I is equal to j, you get 1. Right? So sigma 1 square is 1, sigma 2 square is 1, sigma 3 square is 1. So that's given by delta ij. Is that clear? If I is equal to j, it is 1. And if I is not equal to j, it gives the third one. Ijk sigma k. This is a short form of writing or a compact way of writing. This is a compact way of writing. Sigma 1 square is equal to 1. Sigma 1 square is equal to 1. Sigma 2 square is equal to 1. Sigma 3 square is equal to 1. That's your I is equal to j. If I is not equal to j, that's sigma 1 times sigma 2. It is cyclic 1, 2, 3. Sigma 3. I, right? That's your epsilon ijk property, right? That gives you that. Sigma 2 times sigma 3 is equal to I times sigma 1. And sigma 3 and sigma 1 is equal to I times sigma 2. This is writing this explicitly. That's what this is, a compact way of writing these 6 of them. If you want sigma 2 times sigma 1, also I can. Right? If you want, this is also there, right? So there are 9 pieces in there. So sigma 2 times sigma 1. So this is going opposite. So it is minus I sigma 3. Right, because this is 2, 1, 3 now. And sigma 3 times sigma 2 is equal to minus I sigma 1. And sigma 3 times sigma 1 is equal to minus I sigma 2. Okay, any questions? Again, these are the 3 defining quantities. And
sigma 3, sigma 1 is cyclic.
oh, no, there's a minus, right? What's the question again? Tell us.
That's with plus sigma 3 and sigma 1. No, at this side.
This one? Oh, I wrote it wrong. Sigma 1, sigma 2, right? I was switching all of them. Yeah, you're right. Okay. So now it is not cyclic, right? 1. If it is not cyclic, then you increase minus 1. Notice that in this definitions, does it say anywhere this is 2 by 2? No, right? So this is a solution of these 3. One solution. They're not at all unique. Okay? This is one solution for this. It is not unique at all. And now what we will do is we will try to get a most generic one where this is one of them. So we want to find a solution in that sense. Is that clear? This is an example. It satisfies this these 3 conditions: traceless, Hermitian, and this is called algebra of angular momentum. Let's in the last 5 minutes, let's try to get a few more properties of this. And notice again, I'm not using this. Whatever I have written down after this line, I have not used. I'm restricting only to algebra itself. So let's try to find out what is sigma 1 comma sigma 2. And this brackets mean commutation relation. So this is sigma 1 sigma 2 minus of sigma 2 sigma 1. But we know this sigma 1 sigma 2 is I sigma 3 by the algebra, and this is sigma 2 sigma 1 is minus of minus I and sigma 3. So that's 2 times I and sigma 3. In fact, why do it one by one? Let's try to do this right away using this whole equation. If I have any arbitrary I and j instead of 1 and 2, so this will be equal to sigma I sigma j minus of sigma j sigma I. Right. So now let me do this. So this is sigma I sigma j is this. Right? So this is delta ij plus I epsilon ij k sigma k minus of sigma j sigma I is I flip j and I positions. So this is delta ji plus I epsilon jik sigma k. Is that clear what I did?
Yeah.
Like I just flipped the j and I, that's the definition, so I flip. That's equal to still work. That's delta ij minus delta ji plus I 1 ijk sigma k minus I epsilon jik sigma k. Kronecker delta symbol is symmetric in under its indices. If I swap it, it should not change. So these two are the same quantities. Right? So they cancel out. That's equal to 0. And Levi-Civita symbol is antisymmetric under a swap of two indices. So if I swap j and I get a -1, which will make this a plus, and then they will add up. Right, so it is 2i. So it's 2i epsilon I k sigma k. That's a general result now for any sigma I, sigma j. There is another product. So this is commutation, right? So this is a commutation relation. If I write curly brackets instead, that's called an anti-commutation relation. That just means this is plus definition of a anti-commutation. Is that familiar? No?
This one is familiar.
Yeah, this one should be familiar, right? That's this is an anti-commutation relation. This shows up in Dirac equation. Is Dirac equation, when I say Dirac equation, is that a familiar term?
A little bit.
So the idea is, very broadly speaking, we have relativistic mechanics and non-relativistic mechanics, right? Let's start with non-relativistic mechanics. That's the mechanics before Einstein. That's Newton's law. So you start with Newton's law and then you quantize it, right? You get Schrodinger equation, right? And that's non-relativistic quantum mechanics. You can start with Einstein's equation instead of Newton's equation and then quantize it. You get relativistic mechanics, and that's Dirac equation. So relativistic Schrodinger equation, in a sense, is Dirac. like, or Dirac, sorry, Schrodinger equation is non-relativistic, Dirac equation is relativistic. So that's the, and there this anti-commutations are kind of shows up everywhere here. There is a whole subject called Clifford algebra, which works with the commutation relations and anti-commutation relations. So it's kind of, if you do a little bit more of quantum mechanics, you will see it. But anyway, so what is this equal to? This is the same thing as here, but now what happens is this is a plus sign, right? When this is a plus sign and you flip this, these two cancel out and these two add up, right? So it is 2 times Q delta ij. It's kind of straightforward. So and these are called anti-commutation relations. Anti-commutation relations are very important because 1 minute I can tell it. Again, as a general knowledge, we have, suppose we have an electron and there is another electron, let's say 2 electrons in my 2 hands, and then I interchange them. What happens? Let's say in the universe, there's just 2 electrons. Will I be able to sense it, let's say? Is there a difference between 2 electrons? Is that clear? So suppose there is a red ball and there is another red ball. If they're perfectly identical, you blink your eye and they replace it, right? And you will not be able to tell the difference between the two. But let's say now there are 2 electrons, okay? They look completely identical. Or are they identical? The question is, are they identical? If I swap them while you blink your eye, will you be able to tell the difference? Or what will you look for to tell the difference? Spin, yes. So it's Fermi-Dirac statistics. There are 2 statistics, Bose-Einstein and Fermi-Dirac. Bose-Einstein statistics is built out of the situation that there are identical balls, right? And you interchange, or what is the permutations of getting them. That's Bose-Einstein, and that works for photons. Photons are identical. You blink your eye and you start to photons, you cannot tell the difference. Electrons you can, because of the spin, exactly because of the spin, because they satisfy Fermi-Dirac electrons. That means to say that if you have 2 products, they have to satisfy this algebra, right? And then what we are talking about here is that you want to talk about 2 numbers, A and B, or 2 quantities A and B, AB plus BA. So what happens is that, or more precisely, when I swap the 2 electrons, most of the things remain the same except the sign. Again, the parity changes. That's what you would say.
Pauli exclusion principle.
That's a consequence of that. Pauli exclusion principle is mostly empirical, or he could realize that this is there. So very elegant. But that's exactly, it's a consequence of the wave function swapping sign. So that means to say that AB is equal to minus BA, right? Which means that this has to be equal to 0. And then you say that what satisfies this? Does normal number satisfy this? Like 2 times 3 plus 3 times 2. Now that doesn't satisfy, right? And then you say even matrices, can you think of matrices that satisfy this? Even matrices don't satisfy this, okay? Like it's not easy to construct a set of, or algebraically speaking, it's not easy. So this is called Grossman algebra. This is a new kind of numbers. Very counterintuitive, right? Product of 2 numbers, you swap them, has to be equal to 0. It is too restrictive. So there's a like it's almost like binary. You, for example, if this was A square is 0. There is a number if you multiply by, if A is equal to B, for example, you multiply by itself with 0. Right? So it's too restrictive in that sense. So Then you build algebra out of it. It is possible to, there are such numbers, but then these properties are not at all like normal numbers. So if you want to work with electrons in the clearest sophisticated way, then you cannot work with normal numbers. So wave functions are not normal numbers, like under statistics, when you, as an operator, when you start them, they respect that. So they have to be gross numbers. So that's just for information. We won't be able to discuss those things here, even in a normal quantum mechanics course. It is a very high advanced level do. But it's good to, at least you should be aware of it. So that's good. Okay, that's all. Thank you. Next week onwards, or after the exam, we will really pick up speed. I guess we shift to speed.